Okay, hi. We will go through the actual method to solve those system of nonlinear equations. That is one of the methods used by R. And there will be videos to how to use R to actually do this. It's not as simple as LM um, for various reasons. Okay, let's just talk about the algorithm because we want to get an understanding. So it's called the Gauss-Markov method, and it's for getting an approximate least squares estimate for gamma. Okay, so we're gonna call it G, our least squares estimate, and it's not going to be exactly the one that minimizes Q the absolute most, but with very high probability, um, it will converge to the one that does minimize it. Um, so we talk about the algorithm now. Okay, so this is clear. This is the model. This is some function, nonlinear, and this we'll call yi hat, the fitted value. And I am just replacing gamma, which is unknown, with g, based on the data, right? G is based on the data, and it's an approximation for the fit that will minimize the least squares error. So G is a vector, okay, to be clear, and Xi is also a vector. To be clear, recall, so we had, just to get all the notation, because I think this is part of it, is X, what would it be, Xi1, there's no 1 here, and Xiq, and G, G0, Gp minus 1. Something like this, okay? All right, so algorithm. First thing, won't be explained at the moment, but we will talk about ways to do this when we get to the example. So the first step is make a guess. So guess, initial guess, G0 initial. Not really a sentence, but we will make some guess for G, and we will improve upon the guess. This is the way a lot of numerical methods work. Okay? Okay, that's it. That's the first step, and more on this, more to come. So this is an important step. It doesn't sound like it. You just make a guess, but let's just make sure we're clear. More later. Okay, 2. So we make a Taylor expansion. So by Taylor's theorem, multivariate version, we can write where these squiggles are to be loosely interpreted, because it might not be, I could be more careful and write an equals and put stuff over here, but I'm just going to be loose with this. So this, we want to approximate this nonlinear function with a linear function. So we're going to have a hyperplane over here. So you can think of this as a constant value. This is a scalar, f, and I'm really thinking of gamma, this is a constant, so I'm really thinking of this almost as the parameters, and this is the variable. The gamma is the variable. So I'm thinking of this function, a scalar function of a vector independent variable gamma, and I'm going to expand it with Taylor's theorem. Okay, so I get f. I'm going to start with my guess, G0. This means the vector, initial vector, okay? So G0 is initial vector, and this means every entry has to be guessed, right? Okay, plus, and now I have my sort of tangent term, and since we're potentially multivariable here, we have k equals 0 to p minus 1. And we have these p terms, so I have the partial derivative of f xi gamma with respect to gamma k. And I evaluate this at gamma equals g0, my guess, and now times the distance I'm moving away from gamma. So how far have I moved away from gamma here? I mean G0. This is my center. And now I want to claim this is what it is here. So it's the difference between these two, right? So it should be gamma minus G0. Gamma K minus G0, okay. Yeah. The distance away, the slope. So this is a linear, it's a planar approximation to this function. It's accurate at G0 and near G0. Okay, so this is my replacement here. Okay, now we make some notation changes just so we can see things a little easier. So we have, let's let Fi0 equal F, just to simplify this notation. Okay, let's let dik0 just equal this whole piece, right? But add this one for the kth one, right? So this is dik0, yeah, is going to be df xi gamma d gamma k. So the kth, the partial derivative with respect to gamma k evaluated at, and at the vector x at I, evaluated at gamma equals G0. Okay? So this is just to shorten all these. So you see this is just this is just this, and then we'll call beta K0 this piece here. So gamma K minus GK0. This is just a number, an estimate. This is a parameter, unknown parameter. This is an unknown parameter. So they're playing the roles of these different things. So now if I take Fi0, which is an approximation for F here, and subtract Fi0 here, I get this leftover piece here, right? This leftover piece. So we have yi, then 0. I'm going to define this new thing. yi0 is equal to yi minus fi0. And this is just the rest of the stuff over here. And this is approximately equal to, because there is actually other stuff here. It's not exactly true. If it was, it wouldn't be nonlinear. So this is approximately equal to this summation, this whole thing here, which we can write as a summation, or you can write it using vectors and matrices. So we'll just write it like this now using our notation. So 0, p minus 1, I have d ik0 and b k0. Okay, look, this is it. This is where we wanted to get to. We have the response minus the function here. So I just have a new response. And over here, I have something that's unknown, a parameter. And here I have a constant. Okay, this constant's based on the guess. Right? It's based on the guess, partial derivatives. And the gamma's gone from here, right? Because I evaluated it here at G0. So this is a constant times unknown parameter equals response. It's an MLR form. So this is the big aha moment. Well, we knew this was going to happen. So this is MLR form. Okay, so the next step is find LS estimate for, let's call it MLR here, for MLR. Okay, for yi0 equals this here. Okay. Well, we're getting there, so I don't think we need to get too upset here. We're in good shape. Of course, it's maybe multiple linear regression, so we want to go to the matrix form here. So let's just put everything in linear algebra. So let y0, so the i's are going to go away basically, equal, this is just the y0 here is just the vector form of this. So this is just y1 minus f10 down to yn minus fn0. Okay, let d0 equal, and I need a k here, I think, right? No, I'm going to put all the k's in here because I have a sum. So d0, it just has all the k's in here. So this is d1, 0, 0, right? d 1, p minus 1, 0, and then d n, yep, sorry, 0, 0, and d, yep, n, p minus 1, 0. Okay, so this is a matrix. What else do we have here? We have beta 0. Beta would just be equal to gamma 0 minus g 0, 0, and gamma p minus 1 minus g p minus 1, 0. That's beta. This is your new parameter vector. This is like your new x vector, constants. This is your new response vector. Okay, but everything's set up just like before. So least squares estimate. So least squares estimate to y0 equals d0 beta 0 plus epsilon, another vector. You can think of epsilon as a vector of error. So the least squares estimate to this is as before, b, let's call it 0, equals d0 transpose d0 inverse d0 transpose y0. And we found it. So what did we do? One quick step and a guess, and then we used our old method where we used linear algebra. We just used this formula, and we have an estimate for B0. Now, of course, B0 is an estimate for beta. So what would the best estimate for gamma be at this point? So best estimate for gamma after single step is, well, we have B0 equals gamma 0. No, gamma doesn't, just gamma minus G0. So the answer is gamma B0 plus G0. Okay, it's still just an estimate. So what would you do next? Well, if it should have improved itself, right? So we iterate. So now set G1 equal to gamma, right? Or equal to the estimate of gamma, B0 plus G0. We got to stop in a second and iterate. Okay, so this is what we do. We iterate, we do it again, okay, and we do this until we have a stopping condition. So until stopping condition. This will be when, say, the G's get all converge to the same number, or we can use the SSE, and when that gets some small value or just seems to converge, then we stop, okay, until stopping condition. So we'll talk about that next time. I have to stop the video, though. Click on the next video.